Boker Tov and good morning everyone. My name is Ophir David and welcome to a new video lecture series about inner product spaces. Now inner product spaces is a mathematical subject which at least in my opinion is one of the more interesting one out there, because on the one hand it is still on the easier side of mathematics. We'll see there's lots of intuition and not too much technical stuff. And on the other side, there's lots of interesting structures out there, lots of interesting results. But most importantly, there's lots and lots of applications, both inside and outside of mathematics. So let me just give you a couple of them to have a taste of what we can see. Okay, so the way that I think about inner product spaces is as the meeting point of algebra and geometry. Now, what do I mean by that? We live in a three-dimensional world, which, as we are taught in basic linear algebra course, this means that there are three directions, and they are linearly independent, which are used to define any point in space. However, usually we don't just take any three directions, we take something which looks like that. Right? We have any two directions are perpendicular, they have 90 degrees angle between them. Right? We add a little bit of geometry, and suddenly our choice is much more rigid. Right? We see something like that. Now once we have this geometry, once we have these angles, then we can put these angles in other places. For example, we can take shapes like this right angle triangle, and something that we all know about these sort of shapes is that if we put x, y, and z next to the sides of the triangle, these are its length, and then we put a square near x, y, and z, then the sum of the areas of the squares next to x and y is the area next to z. Right? Or in other words, we just get the Pythagorean theorem. So again, we added a little bit of geometry, we added this 90 degrees angle, and using this geometry, we got a very nice algebraic equation, the x squared plus y squared equals z squared. Okay, so this is the meeting point of geometry and algebra. So this type of result, the Pythagorean theorem and others similar to it, gives us the standard geometry on the plane, the standard geometry on the 3D space, which we usually call the Euclidean geometry. And we have lots and lots of intuition about what happens there because we basically live inside this geometry. And what mathematicians try to do with inner product spaces is to say, we have lots of intuition there. Can we take the intuition from the Euclidean geometry? Can we take the results from the Euclidean geometry and apply them in other places which don't look very similar to it at first? So let me give you a few examples. So one thing that engineers like to talk about are signals, which are basically functions over the real line, like the ones that we see on the bottom left. And we use them to model lots and lots of stuff, like position or speed or acceleration or force, or maybe this is just an electrical wave, or maybe a brain wave, or maybe just model something in the stock market. Right? There are lots and lots of stuff which are basically functions over the real line. So we really want to understand these sort of signals. And one of the main tools that we have is saying that, you know what, this signal looks very complicated, but if I can decompose it, if I can write it as a combination of very simple signals, and I can understand each one of them separately, then maybe I can understand the original signal as well. So for example, in this case, I can write it as a sum of three wave functions. Each one of them are a basic wave function, a sine function, but with different amplitude, different frequency, and maybe different phase. I think that one of them is actually a cosine function. And you might not like trigonometric functions, but they're actually very simple function to work with. So again, if I can understand each one of them separately, then I can understand the original function. Now I claim that we have something very similar in the Pythagorean theorem, because basically there we wanted to understand the z side, which is in a sense more complicated, and we decompose it into the x and y sides, which are in a sense simpler because they are aligned to the main axis. And we said that if we know each one of them separately, then we also understand z, because z squared equals x squared plus y squared. So again, we have this similarity, but it is not just philosophically. We can actually transfer idea from the Pythagorean theorem, from the standard Euclidean space, and apply them to signals. So again, think about it. If you just look at the signals, there are no 90 degrees angles, there are no triangles, but you can take all the intuitions that you have from the 2D and 3D space and apply it there. So this is one of the very strong applications of inner product spaces. And this decomposition of signals is what we call the Fourier transform or the Fourier analysis. And it is one of the stronger tools that any engineer should have. Okay, so this is one application. Let's see another one. And this time in machine learning. So one of the most basic problems in machine learning is the problem of generalization. So for example, let's say that I want to understand how the height of a person depends on its age. So I go and collect lots of data. So I collect ages and heights of different people. And then I want to understand how to generalize it, meaning I have a new person and I know its age, and I want to understand what is going to be its height. I want to guess the height. So this is just one example. I can take other examples, like I want to understand how much fruit I get from a tree depending on how much I water it, or how well I can study depending on how many hours I sleep at night, all sorts of functions like that. So again, in general, we should think about it as some sort of function. I give you x and I want to know what is y, what is f of x. So I can, for example, plot it in a plane and see something like that. And the problem of generalization means that I give you a new x and I need to tell you what is my y. What is my point on this black line? One way of solving this problem is as follows. We look for a good line approximation for this data, like this red line. And if we have such an approximation, then we have a good guess for the generalization. Just take the intersection of the black line and the red line. So again, if we have a good approximation, whatever this means, then we have a good way of generalizing it. Now, if we look at this problem, which again, this is the most basic problem in machine learning, there are no 90 degrees angles. There is no triangles there. But again, I claim that this is a almost straightforward application of the Pythagorean theorem. This is actually going to be one of the first applications that we will see. And using the Pythagorean theorem, using the intuition that we have from standard to this space, we're going to show that not only there is a line, there is a unique line, and we're going to show how to find it. So this problem in machine learning, calling linear regression, is one of the actually first applications that we're going to see. Okay, so let's see another application for machine learning, or more specifically from computer vision. Let's say that you are given some data set of images and you want to understand it. Now, what do I mean by understand? You want to do maybe face detection or face recognition, or maybe you have a face and you want to understand whether it is a happy face or sad face or an angry face. And this sort of question. And the question is, how do you even approach this sort of problem? So one stupid way of doing it is to say, let's choose a pixel and let's look at the same pixel in each picture. And this pixel gives us a number, right? This is the value of the color. And maybe we can use this number in order to say something about the face, right? Maybe it is a happy face or an angry face. And in general, this will not work, right? Because one pixel is not enough to say something about the whole picture. So it doesn't give us too much information. However, can we do something similar but in a smarter way? Can we extract from each image a number or a set of numbers, which the machine learning people call features, and use these features in order to say something about the images? For example, is it a sad face or a happy face? So apparently there are these sort of algorithms, and one of them is called the principal component analysis, or PCA for short. And if you run PCA on this set of images, you get something which looks like that. So for me, if I look on these features, and the first feature, the one on the top left, basically tells me how much light I have on the image, right? Whether I have a lots of light or little light. The second feature tells me whether the light is coming from the right or coming from the left. The third feature tells me if the light is mostly on the face or mostly on the background. And each one of the following feature, you can decide for yourself what it tells you. And again, when I ran this principal component analysis algorithm, I didn't tell him in advance, find me features which are connected to light. Right? I just told him to just run and give me whatever you can give. And again, these sort of numbers are straightforward application of what we're going to see in the inner product spaces. And again, you look on these sort of problems and you don't see triangles, you don't see 90 degrees angles, you don't see anything which looks like the standard Euclidean geometry. However, once you model it in the right way, we can see that we can take the intuition from the standard Euclidean geometry and apply it. Okay, so I hope that by now I convinced you well enough that there are lots of interesting applications of inner product spaces. And even if you don't see the connections, there are many times that there are connections. And we will see these sort of applications along the way inside this course. As I said, the linear regression we will see quite fast. This is one of the first applications. The one about the signals, the Fourier analysis, we will see parts of it, but this is a mostly an infinite dimensional spaces. And in this course, we will touch mostly the finite dimensional ones. And the one in the computer vision, the one about the principal component analysis, will be an application near the end of this course. Okay, so I will go into more in-depth application in the next video, but for now in this video I want to talk more about the format of this course and a little bit about the material. So let's go there. Great. So this is going to be a mathematical course. So first of all, we're going to talk about results and tools, because again, we want to use these results, we want to use these tools in order to apply them in other places. And the second thing is, of course, we're going to talk about proofs, right? Now, if you're studying mathematics, I plan to give all the proofs needed in this sort of course about mathematics. However, if you're not studying mathematics, if you're in engineering, if you're in computer science, maybe in electrical engineering, this sort of stuff, then I'm going to put the more advanced stuff or the more technical stuff in standalone videos. I still suggest that you watch them, but if you want, you can skip them. Okay, so these are two things about mathematics. The third thing, which is really important for me, that every result, every theorem, I want to give both intuition and motivation. These are really important. Intuition is basically, why do we think that this result is going to be true? And motivation is, why do we care that this result is true? Right? These are two very important aspects of every new subject that we learn. And I will hope that you make sure that I keep my promise and actually give intuition and motivation for each one of these resultant tools. Okay, so after the mathematical part of the course, we'll also have lots of applications, like I just mentioned, and again, both inside and outside of mathematics. Some of them I will just mention briefly alongside the standard videos. Some of them will be much more in-depth, much more detailed, and I will put them in a standalone videos. So if you're not familiar with the subject, or if you're just in a hurry to learn the other material, you can just skip them. However, again, they will be, I think, really interesting, and you can treat them as motivation to learn these new subjects. The third thing that I'm going to do is talk a lot about programming. I really believe in an active learning and not just passive listening to someone else. And I think that in mathematics, one of the way to do really good active learning is using programming. And I will use them both as coding exercises and as visualizations. So the coding part is just, I don't know, you can take some sort of new theorem, some sort of new algorithm that we learn in this mathematical course, and just program it into a computer and see what happens. The second one is visualizations. We want to really understand what happens. So like I did before with the features when we want to learn images. So this is the third section. And the fourth one is the notes. And this is the only one which I'm not going to have right now because I don't have notes, at least not in English. But if and once I do, I will give links to them in the descriptions on the video. In general, I'm going to have lots of links in the description of the video for the programming, for the applications, and for all sorts of other stuff. I don't know, maybe I missed something in the video itself and I wanted to add something, and it will be in the description of the video. Okay, so this will be the format in general. Let's talk a little bit more about the actual material. So we start with the requirements for this sort of course. So the first step is linear algebra. You cannot escape basic linear algebra. You need to know sort of stuff like vector spaces and bases and linear transformations, and a little bit more advanced stuff like eigenvalues and eigenvectors and diagonalizations. These are really, really important and will give lots of intuitions about them. So you must know linear algebra. The geometry part, you only need to know a little bit. You need to have a bit of familiarity, like you need to be familiar with distance between points, which is the square root of the sum of squares, or in general, you need to know the Pythagorean theorem. And again, you just need to know that. You don't need to know the proof, but you need to be familiar and you need to be comfortable with it. So these are the main requirements for learning this course. Other than that, some stuff which are useful to know. So as I said before, I'm going to go a lot into applications, both of inside and outside of mathematics. And if you if you're already familiar with this subject, then it can help you. So for example, it will be from calculus and probability and algorithms, in particular graph theory, and outside mathematics, stuff like machine learning and computer vision and all sorts of numerical algorithms. And again, if you're familiar with them, then great. If you're not, you can treat them as a motivation for this course. And these are stuff which are useful to know. You don't have to know them, but useful. Okay, so this is what we need to know in order to study this course. And next is what you're going to know by the end of this course, right? Or in other words, the syllabus. So first of all, we're going to talk about inner products and norms, which are the generalizations of, in a sense, the angles and distances in other vector spaces. We're going to talk about orthonormal basis and Gram-Schmidt process. We're going to talk a lot about special matrices like orthogonal, Hermitian, and normal. And these are very important because in a lot of places which they talk about stuff from inner product spaces, they don't actually mention it, but actually talk about the more technical side of it. And usually the more technical side of it is just talking about matrices or all sorts of matrix compositions. So this will help you to, I don't know, read sort of sources and understand that there are actually inner product spaces in the background. There's a lot of geometry, there's a lot of intuition that you can learn. And on the other hand, if you have some sort of result in inner products and you want to actually program it into a computer, usually it is easier to go to matrices. So this is a very important part. Finally, the crown jewel of this course, the main theorem of this course, is the spectral decomposition theorem for normal matrices, whatever they are. And this will be the final theorem of this course. And it is really, really strong because the result itself is really, really strong, but also because you can apply it in many, many natural cases. For example, a symmetric matrix, which you already know from standard and basic linear course, is a normal matrix. So for example, the spectral decomposition can be applied for any symmetric matrix. And we will see that you can really apply it in many, many other places. Okay, so this is what we need to know in order to study this course and what we will know by the end of this course. And finally, where does it all lead? So first of all is what I mentioned before, is the Fourier analysis, is the Fourier transforms, which is basically inner products on infinite dimensional spaces. This course specifically will be mostly about finite dimensional spaces, though some of the results can be applied in infinite dimensional cases. However, once you go infinite dimensional, you need to add a little bit more calculus into it. So this is the Fourier analysis. Second place is all the numerical algorithms and the machine learning. Lots and lots of applications of inner product spaces. Another place that it will read if you're students of mathematics is group representations. And I think this is one of the really interesting parts of mathematics, and most people outside of mathematics don't really know about it. For example, lots of engineers know Fourier analysis, but they don't know that Fourier analysis is just a specific case of group representation. So if you're a student of mathematics, this is a good place to continue. And finally, not exactly place to continue after inner product spaces, but actually something which completes inner product spaces. So as I said before, the spectral decomposition theorem for normal matrices can be applied in many, many natural cases, however, not in every place. And in the places where you cannot apply it, usually you can apply the Braun-Frobenius theorem. So for example, I said before that symmetric matrices are normal matrices, so you can apply it there. However, if your process is not symmetric and you still want to apply something like the spectral decomposition theorem, then usually you use the Braun-Frobenius theorem. So this is sort of a way to complete this theorem. Okay, I think that this is enough for the sort of very, very early introduction to inner product spaces. Next time I will give a more in-depth application and more detailed in how it connects to algebra and how it connects to geometry. And the video after that, we will actually start the standard material of the course. Okay, so I will see you next time.